For this portion of the lecture, I've gone back through and taken some hand notes to go through some of the governing equations for conduction, convection, and radiation throughout Chapter 1. So the first thing we're going to look back at is conduction, and we're going to look again at Fourier's law. So this again, we call our heat flux here is equal to our negative K times dt dx. So another way to write this here, our heat flux is equal to our K value here, which is our thermal conductivity value right here. And this is times our temperature difference between T1 and T2 divided by our L, which is the distance in our x direction here. Or this is also equal, we can write our T1 minus T2. You may also see it as a delta T as well. So a couple different ways to see this. You may see T1, T2 over L, delta T over L, or dt dx. So three different ways you might see that in different problems there. I wanted to address all of those. We have our heat flux here, our qx double prime. This is the heat transfer rate in our x direction here. This is going to be in units of watts per meter squared. Our K being our thermal conductivity in units of watts per meters times Kelvin. Our delta T here is our temperature distribution, units here of Kelvin. And our L is our distance in our x direction here in units of meters for this case here. And Q of x is the heat rate and units of watts. So unit analysis is very important as we go through this. Make sure you put things in the right units, especially if we're given values. They gave us to in centimeters, you need it in meters. They gave us in Fahrenheit, we need it in Kelvin, things like that. Make sure we do the appropriate conversions and always double check with our unit analysis here. We can say, okay, if our heat rate is in units of watts per meter squared that we see from up here, and we're multiplying our K value here, by our delta T over L right there, we can go through and say, okay, there's our values here that we're plugging in right here. This is our watts per meters times Kelvin, which is our K value units right there. And we can see our delta T over L is going to be in units of temperature right here, is going to be in Kelvin, and L is going to be in meters. So we can double check, do our unit analysis, that cancels there, move things around, or watts per meter squared is equal to watts per meter squared, double check. So that's something that you're going to want to do for all these different problems. Make sure you do your unit analysis out. Keep track of your units throughout the problem. It's a great way to double check that you're using the right equations and plugging things in correctly. Another side note down here, if we're talking about heat rate, our heat rate or our Qx value right here is in units of watts. This is in units of watts here. We can double check that we can see, okay, if I take my heat flux value right here, my Qx double prime, times my area, where area has units of meters per squared, and our heat flux, we can see up here, is in watts per meter squared. See, our meters squared are going to cancel with our meters squared right there, just leaving us with a value of watts. So watts is equal to watts, double check. Yes, this is an appropriate conversion to go from our heat rate, to get our heat rate value from our heat flux times our area. So again, I make a little note down here, to get heat rate from the calculated heat flux, we need to multiply by the area of our surface right there, our A value. So this is dealing with conduction, talking about a couple different ways we may see Fourier's law, our unit analysis, and all the individual variables we might be using. So now moving on to convection. For convection, we're going to be utilizing Newton's law of cooling. If we go back to our textbook, this is equation 1.3a from our text for this here. And this is our governing equation right there. Our heat flux is equal to our H value, or our convection heat transfer coefficient, times our T sub s minus T sub infinity, where T sub s is our surface temperature, and T sub infinity is going to be our fluid temperature right there, T sub s, T sub infinity right there. So this is Newton's law of cooling right here from 1.3a in our textbook to get our heat flux right there. So we can do a unit analysis out here. We can say, okay, the units for heat flux again are watts per meter squared. Our H value here has units of watts per meter squared times Kelvin. There's our watts per meter squared times Kelvin. And we can see down here, now our last thing right here is Ts minus T sub infinity, which is going to have units of Kelvin for temperature right there. Our Kelvin cancels with our Kelvin right there. And what we can see here is we have watts per meter squared is equal to watts per meter squared. This doubles checks out. So this equation does give us the right units for heat flux. So as we move on to our radiation, our governing equation is going to come from 1.5 in our textbook here. We have our E is equal to epsilon times E sub B, where our E is our emissive power, our epsilon is our emissivity, and our E sub B is the emissive power of a black body. So this is our governing equation right here, and we can reference back to equation 1.5 in our textbook for that there. Now, if we're dealing with this here, our E sub B, we can get from our Stefan-Boltzmann law right here. So E sub B is equal to our sigma times our T sub S to the fourth, where our sigma right here is the Stefan-Boltzmann's constant, and this is given to us as a value of 5.67 times 10 to the 8th, and our units are watts per meter squared times Kelvin to the fourth there. Going back up here, our T sub S from this equation here, our T sub S is our absolute temperature there, in units of Kelvin right there. Our E sub B is our emissive power of a black body, and our E value here from our governing equation 1.5 is the emissive power. So now moving on to irradiation. What irradiation is this is the rate at which radiation is incident on a unit area of a surface. So we have our governing equation here, our G sub ABS, or absorbed incident radiation, is equal to our alpha term, which alpha is our surface absorptivity, times G, where G is our irradiation there. We can see our alpha value right here is going to be between 0 and 1 and be unitless here. Our GABS right here, our absorbed incident radiation, has units of watts per meter squared, and G has units of watts per meter squared there. So if this is unitless and these two both have the same units of watts per meter squared, that is our unit analysis right there. Now, we do have a special case that we're going to discuss here when we have a small surface of TS and a much, much larger isothermal surface that completely surrounds the small surface right there. So irradiation may be approximated by emission from a black body at our T surround right there. So this is where we have our Stefan-Boltzmann's law for emissive power right there, where G is equal to our sigma times T surround to the fourth, where we have, if it's a gray surface, our alpha is going to be equal to our epsilon value there, which gives us this governing equation down here. We can see our heat flux for radiation is equal to our Q over A, our heat rate over A, which we've shown a reverse of that before, because if we multiply our flux by the area, we get our heat rate there. So reverse, if we divide our heat rate by area there, we can get our heat flux. So this is equal to our epsilon, E sub B, T sub S, minus alpha G, which is then can be reduced down here to see that this is epsilon times our sigma value right there from our Stefan-Boltzmann constant times the difference between our T sub S to the fourth and T surround to the fourth. And again, this is for that special case with a small surface area and a much larger isothermal surface that completely surrounds it. So now what I want to do is take a look at an example problem for you guys. So right here, we're going to take a look at problem 1.4. In this problem here, they have a problem statement that they give us in words, and also they've included a diagram for us as well. So we need to collect all the information from both the diagram and from the problem statement in words here. So reading through this, it says a chip gives us a width of L is equal to 15 meters on a side and are mounted to a substrate that is installed in an enclosure whose walls are maintained at a temperature that they tell us now of T surround is equal to T sub infinity, which is equal to 25 degrees Celsius. The chips have an emissivity of epsilon equal to 0.6, and a maximum allowable temperature of our T sub S is equal to 85 degrees Celsius. So we have a lot of information just within that problem statement here. We have our L value, we have our T sub surround, our T sub infinity, we have our T sub S, we have our epsilon value, all right there just in the problem statement. We can come down here to the initial given diagram right here, and what we can see here, okay, here's the enclosure, which is our T surround that we can reference back up here to our 25 degrees Celsius. Here is our temperature of our air, our T sub infinity, which is equal to T sub surround, which is 25 degrees Celsius. Then we have these chips that they're talking about here. Well, we know this length of the chip is given to us as 15 millimeters, and then we got to pay attention here. This is in millimeters. So as we plug in, do we want that in meters? Do we want that in millimeters? We can see over here for the chip itself, there's our T sub S, surface temperature right there of the chip of 85 degrees Celsius. And here's our epsilon value right there, emissivity, which is given to us as 0.6. Now, there's two parts to the problem that they want us to solve. They tell us if the heat is rejected from the chips by radiation and natural convection, what is the maximum operating power? So that's what we're looking for, is our maximum operating power of each chip. So the convection coefficient depends on the chip to air temperature difference. That's the temperature difference we're going to be dealing with there, which can be approximated as H is equal to C times our T sub S minus T infinity all to the 1/4 power, where they give us our C value for that relationship right there is 4.2 units of watts per meter squared. So that's part A, the problem that they want us to solve. In part B, they're telling us that the fan is used to maintain the airflow through the enclosure, and heat transfer is by forced convection. And they give us our H value for that forced convection here of 250 watts per meter squared times Kelvin. Now what they want us to calculate here is what is the maximum operating power. So we need to calculate what the maximum operating power is for this right here. Now, the reason I wanted to go over this problem with you guys is to show you a couple different things. One, how to start applying some of the equations we learned within this first section and this first 2 lectures. But also what I wanted to really show and demonstrate with this is how problems can be presented to you. The same problem in a couple different manners. So the first one that we just saw on the previous slide, a lot of the information was given to us in words in the problem statement. Whereas now in this same problem here, what we can see is rather than them actually spelling it out and typing it out there, they give us a rather brief description right here. They just tell us power dissipation from the chips operating at a surface temperature of 85 degrees Celsius in an enclosure whose walls and air are at 25 degrees Celsius for free convection, forced convection. So that's it there. So they don't type out T sub s equals T sub infinity equals or any of that. What they do is they give us this schematic down here. So in the schematic down here, what we can see now is, okay, we have our T sub infinity, we have our H value, we have our T surround, here's our air, here's our surface outside over there, the enclosure, here is our chip right here, here is the length of the chip, here is our T sub s, here is our emissivity, and all that there. So this could be a couple different things. As I just mentioned, this could be a different way to present it, where a lot more of the information is given to us in the schematic rather than the problem statement. Also, what this can be is a great example for you on how I expect you to solve these problems and what I'd like to see. So if you look through the Getting Started section, I've discussed homework format and how I really want a lot of detail, and the format's going to be very important counting towards your grade portion of it. So what I'm saying here is you took all that information that was given on the previous slide in the word statement and you've applied it to your own schematic here for your solution. So this is something that's going to be up to you on how you want to present this material. All this is going to be very, very important for you as you're solving the problem. The question is, how can you quickly and easily write this all down and reference back to it as you're choosing your governing equations and plugging things in? So having these all listed out, okay, this is my T sub infinity, this is my T sub s, these are the units, these are the values, this is what it relates to within the problem statement, all that there. So as you come down here now and look at your governing equations here, you're saying, okay, I need my T sub s, I need my T sub infinity, my epsilon, all these values here, and start plugging in. You have a plot, you can go right back up here and say, okay, that's what it is right there. I can quickly plug and chug. So by taking the time in the initial setup of the problem and listing out all of the given information and what they're asking you to solve for, it's going to make your life a lot easier as you're going through and solving this problem. Now, I'm not going to go through the solution right here that's typed out in kind of the abbreviated version of it, but I have posted my hand solution to this problem so you can see kind of what I expect from you as far as where are your givens, what is your initial diagram, what are they asking you to solve for, here's my governing equation, here's my thought process along the way as I'm solving out this problem. So please reference the PDF document attached to this within the module to reference my hand solution to this problem 1.4.